Welcome to this coding walkthrough. Today, we'll explore problem number 557, reverse words in a string 3. This problem challenges us to manipulate strings efficiently by reversing each word while maintaining the overall structure. Let's dive in and break it down step by step. In this problem, we are given a string S that is made up of words separated by single spaces. A word in this context is defined as a sequence of characters that are not spaces. The task is to reverse the characters of each word while keeping the order of the words and the spaces between them exactly as they are. Once we reverse the characters of each word, we return the resulting string. The input will be a single string S, which can include English letters, numbers, punctuation, and spaces between words. However, there will be no leading or trailing spaces in the string, and words will always be separated by exactly one space. The output is also a single string, with the same words as the input, but each word's characters reversed. Let's start by looking at an example to make this clearer. In the first example, the input string is S equals let's take LeetCode contest. After splitting the string into words, we have the list, let's take LeetCode contest. Reversing the characters of each word produces SAL, ikat, idotl, setnok. When these reversed words are joined back together with spaces, the result is the string SAL ikat idotl setnok. This is the final output. Another example uses the input S equals God ding. Splitting it into words gives God ding. After reversing the characters of each word, we get dog nid. Joining these reversed words with a single space results in the output dog nid. Now let's look at a third example. Here, the input string is S equals hello world. The words in the string are hello world. When we reverse the characters of each word, we get the list ala durao. Joining these reversed words with a single space gives the output string ala durao. This process remains the same for any input string. We split the string into words, reverse each word individually, and then join them back together with single spaces. The constraints of the problem ensure that the string S will always have a length between 1 and 50,000 characters and will only include printable ASCII characters. Additionally, the string S will never have leading or trailing spaces, and there will always be exactly one space separating the words. Some edge cases to consider include single word inputs, where we simply reverse the word itself. For instance, if S equals hello, the output is ala. If the string includes punctuation, such as S equals hello world, we treat punctuation as part of the word. The output in this case would be ala durao. Similarly, if the string contains numbers, we treat them as part of the word. For example, S equals ABC 123 def 456 would result in the output 321 CBA 654 fed. These guidelines help ensure that we handle all possible inputs correctly. To begin, let's consider a brute force approach, which is often the most intuitive method. The idea here is straightforward. We split the input string into individual words using the space character as a delimiter, reverse each word, and then rejoin everything into a single string. The process can be broken into three main steps. First, by using Python split method, we get a list of words. Next, we reverse each word individually, which can be done with slicing or a helper function. Finally, we use the join method to combine the reversed words back into a single string. This approach has a time complexity of O, n, where n is the length of the string, because splitting and joining the string both take O, n, and reversing each word is proportional to the sum of the word lengths, which is also O, n. However, a trade-off here is the space complexity of O, n, since creating a new list for the split operation requires additional memory. While simple to implement, this approach isn't the most memory efficient for very large strings, but it is a good starting point to understand the problem. Now, let's explore an in-place approach that focuses on reducing memory usage. The intuition here is to reverse each word directly in the original string without creating additional data structures. Although Python strings are immutable, this concept is more applicable in languages like C++ that allow in-place modifications. In Python, we achieve a similar effect by first converting the string into a mutable data structure, such as a list of characters. From there, we iterate through the list to identify the start and end indices of each word. Once we have these indices, we reverse the characters between them for each word. Finally, we convert the list back into a string. This approach has a time complexity of O(n), as each character is visited once, and a space complexity of O(1), if we disregard the temporary space used for the list conversion. While this method is memory efficient, the code is more complex and less intuitive than the brute force approach, making it harder to implement and debug, particularly in Python. Additionally, we can consider a two-pointer approach, which builds on the in-place strategy but optimizes the process further. Here, we use two pointers to manage word boundaries and reverse words on the fly. The process starts by using one pointer to traverse the string. When we encounter a space or the end of the string, we reverse the word that has just been traversed. This is done by adjusting the second pointer to mark the end of the word and applying a reversal only within those boundaries. After reversing the word, we continue the traversal to locate the next word boundary. This method retains a time complexity of O(n), as each character is processed only once. Space complexity is also O(1), making it efficient in terms of memory usage. However, due to Python's immutable strings, this approach is challenging to implement directly, often requiring additional steps to simulate in-place modifications. While efficient, the increased complexity can make this approach less practical for Python developers. Ultimately, the chosen strategy is an optimized brute force approach, which balances simplicity and performance. In Python, the immutability of strings makes in-place operations cumbersome, and the brute force method aligns well with the language's strengths. Splitting the string into words and reversing each word individually is both straightforward and efficient. Python's built-in slicing and join methods are highly optimized, allowing this approach to handle even large strings effectively. The steps are clear: split the string using split, reverse each word with slicing, and rejoin the words into a single string with join. This strategy offers the advantages of simplicity and readability, making it easy to understand and implement. While the space complexity of O(n) is higher than the in-place approaches, the trade-off is worthwhile for the ease of use and the benefits of leveraging Python's built-in methods. In conclusion, the brute force approach provides the best balance of simplicity, readability, and performance for this problem in Python. While it may not be the most memory-efficient option, its straightforward implementation and compatibility with Python's strengths make it the most practical choice. This method leverages optimized built-in functions and avoids unnecessary complexity, making it an excellent solution for reversing words in a string efficiently. To solve this problem, the goal is to reverse every word in a given string while keeping the words in their original order. For example, given the input string "let's solve this problem," we want to produce the output "sal evlos site melborb." The key here is that the words remain in the same sequence, but the characters within each word are reversed. To achieve this, we can break the solution into 5 key steps. First, we handle the input string by checking for edge cases, such as an empty string. If the input is empty, we return an empty string immediately. Next, we split the input string into a list of words using Python's split function, which uses spaces as the default delimiter. For instance, splitting "let's solve this problem" results in the list of words, "let's solve this problem." Once we have this list, we can focus on reversing the characters of each word. The next step involves iterating over the list of words and reversing each word individually. This can be done efficiently in Python using slicing with the syntax word ::-1. For example, reversing the word "let's" produces sal. Similarly, solve becomes evlos, and so on. After reversing all the words, we then rebuild the string by combining the reversed words back together. This is done using Python's join function, which merges the words into a single string with spaces separating them. For example, joining the reversed words "sal evlos site melborb" results in the final output string "sal evlos site melborb." The last step is simply returning this reconstructed string as the result. This approach is efficient because Python's slicing mechanism for reversing strings and its built-in methods for splitting and joining are optimized for performance. Now, let's look at the data structures and complexity analysis of the algorithm. The input is a single string S that contains the words to be processed. As we split the string into words, we temporarily store them in a list called list_of_words. This list allows us to iterate over and manipulate the words efficiently. Once all words are reversed, we use the join function to produce the output string. This reconstructed string is then returned as the final result. From a complexity perspective, the time complexity of the algorithm is O(n), where n is the total number of characters in the input string. Splitting the string into words takes O(n), reversing each word cumulatively also takes O(n), and joining the reversed words back into a single string is another O(n) operation. For space complexity, the algorithm uses O(n) space to store the list of split words and the reconstructed string. These efficient operations ensure the algorithm handles even large strings effectively. Lastly, let's explore some edge cases and how the algorithm handles them. For an empty string input, such as, the algorithm immediately returns an empty string since there's nothing to process. For a single word, like hello, the algorithm works seamlessly, reversing the word to produce all h. When the input contains multiple spaces, for example, hello world, Python split function automatically removes extra spaces, so the reversed output becomes all h to row w with the same spacing preserved in the output. Special characters are also handled properly. For instance, in the input hello world, the punctuation is treated as part of the word, resulting in the reversed output all h to row w. Overall, the implementation is robust and accounts for these scenarios effectively. Here's the Python implementation. We split the string, reverse each word using slicing, and join the results to produce the desired output. This solution is designed to reverse each word in a given string while maintaining the word order. Let's break it down step by step. 1. First, the input string s is split into a list of words using the .split method. This method separates the string wherever spaces occur, creating a list of individual words. 2. Using a list comprehension, each word in this list is reversed. The slicing syntax word, ::-1, is used to reverse the string. Essentially, ::-1 iterates over the string from the end to the start, generating the reversed version. 3. Once all words are reversed, the join method is used to concatenate them back into a single string. The .join, reversed underscore words, ensures that the words are joined with a single space between them, maintaining the original spacing structure. This approach is efficient and concise. The splitting and joining operations ensure that spaces are handled correctly, while the list comprehension makes the reversal process straightforward and readable. The algorithm runs in O(n) time, where n is the length of the input string, as each character is processed once during the splitting, reversing, and joining steps. This solution handles edge cases like empty strings or strings with multiple spaces between words effectively, as the split and join methods manage spacing naturally without additional checks. This is the Java implementation of LeetCode problem number 557, reverse words in a string 3. The solution mirrors the Python logic by splitting the input string into words, reversing each word, and then joining them back with spaces. In Java, we use String Builder to handle string manipulation efficiently. The split method is used for extracting words, and the reverse method of String Builder is used to reverse each word. Finally, the results are appended and returned as a single string. In this problem, we are asked to reverse each word in a given string while preserving the order of the words themselves. For example, given the input string "Let's take LeetCode contest," our goal is to reverse each word individually but keep them in their original positions. To solve this, we start by splitting the string into a list of words using the split method. This method breaks the string into smaller parts wherever it finds a space, resulting in a list. Let's take LeetCode contest. Now that we have the words isolated, the next step is to reverse each word. We can accomplish this efficiently using a list comprehension. By iterating through the list of words and applying slicing with word ::-1, we reverse each word in place. For instance, as we process the word let's, it becomes SAL. The same logic applies to all other words in the list, such as reversing take to a cat and so on. This gives us a new list where all the words are reversed but still in their original order. Continuing with our example, the reversed words are as follows: let's becomes SAL, take becomes a cat, LeetCode becomes EDOTL, and contest becomes setnock. At this point, our list of reversed words looks like SAL, a cat, EDOTL, setnock. With the words now reversed, the final step is to join these words back into a single string. Using the join method, we concatenate all the elements in the reversed underscore words list, separated by spaces. This produces the final result, STL a cat EDOTL setnock. To reinforce the approach, let's look at another example. Given the input God is great, we start by splitting the string into its individual words, resulting in God is great. In the second example, the list of words is God is great. To reverse each word, we apply the same list comprehension technique. The first word, God, is reversed to dog, is becomes si, and great is reversed to TRG. This gives us a new list of reversed words, dog, say, TRG. Finally, we use the join method to merge these reversed words back into a single string. When we join them with spaces, the result is dog si TRG. This approach works consistently across different inputs, even when the string contains shorter words. For instance, let's now consider the input string ABC. In our final example, the input string is ABC. Splitting the string using the split method gives us the list A, B, C. Here, each word consists of just a single character. Reversing each word individually results in no visible change because a single character remains the same when reversed. Thus, the reversed words are A, B, C. To complete the solution, we use the join method to combine these words back into a single string. The final output is ABC, which matches the input string because reversing single character words doesn't alter them. This demonstrates that our solution handles edge cases like this effectively, ensuring the problem requirements are met in all scenarios. To analyze the time complexity of this solution, let's break it down into its core steps. First, we split the input string into a list of words using the split method. This operation scans the entire string to locate spaces, which means its time complexity is O(n), where n is the total number of characters in the string. Next, we reverse each word using a list comprehension. Each word is reversed using slicing, which requires O(m_i), time for a word of length m_i. Summing this over all words gives us O(n), time again since the total length of all words equals the total number of characters in the string. Finally, we combine the reversed words into a single string using the join method. This step also processes all characters and spaces once, resulting in another O(n) operation. When we combine these three steps, the overall time complexity becomes O(n) plus O(n) plus O(n), which simplifies to O(n). Now, let's examine the space complexity. When we split the string into words using the split method, a new list is created to store the words. In the worst case, if each character is separated by a space, this requires O(n) additional space. Then, during the reversal step, another list is created to store the reversed words, which also takes O(n) space since the total length of all reversed words matches the input string's length. Finally, the join method creates a new string to hold the final result, requiring yet another O(n) space. Altogether, the space complexity of these operations is O(n) plus O(n) plus O(n), which simplifies to O(n). It's important to note that we are not modifying the input string in place, so the space usage is proportional to the size of the input. When comparing this approach to a naive or brute force method, the current solution stands out for its efficiency. A naive approach might manually iterate through the string, identify words, reverse them one by one, and rebuild the string step by step. While the time complexity of this approach could theoretically remain O(n), it would introduce significant overhead due to additional operations and a lack of optimization, making it less practical. In contrast, this solution leverages Python's built-in methods for splitting, slicing, and joining, ensuring that operations are performed efficiently and directly. Additionally, the time and space complexities remain O(n) across all cases best, average, and worst, because every character in the string is processed exactly once during each phase of the algorithm. In conclusion, the solution is both time and space efficient, with an overall complexity of O(n) for both, where n is the total number of characters in the input string. By utilizing Python's optimized string operations, we achieve a streamlined and optimal implementation. This ensures that the solution handles all input sizes effectively without unnecessary overhead, making it well suited to the constraints of the problem. One of the most common mistakes when solving this problem is reversing the entire string instead of reversing individual words. For example, if the input is hello world, some solutions incorrectly reverse it as drowh, which flips the entire string, including spaces. The correct approach is to split the string into words, reverse each word independently, and then rejoin them to form all drowh. Another frequent issue is not preserving multiple spaces between words. If the input contains extra spaces, like Hello World, and your solution merges them into single spaces, the output will be inaccurate. To handle this, you need to carefully split and rejoin the string while preserving the original spacing. Additionally, ignoring edge cases, such as empty strings or single-word inputs, can lead to unexpected runtime errors or incorrect results. For instance, an empty string should return an empty string, and hello should simply become all H. Lastly, inefficient string concatenation in loops can be a performance bottleneck. Using operations like result plus equals word repeatedly creates a new string each time, resulting in O(n)² complexity. Instead, store intermediate results in a list and join them at the end for a much faster O(n) solution. Another mistake to watch for is mishandling special characters like punctuation or symbols. For example, if the input is hello world, your solution might misplace or even remove the comma and exclamation mark during the reversal. Depending on the problem requirements, you may need to treat special characters as part of the word or handle them separately. When preparing for interviews, it's critical to clarify such requirements up front. For instance, confirm whether spaces and punctuation must be preserved before implementing your solution. Additionally, focus on optimizing string operations. If the language allows, in-place modifications are ideal for reducing memory usage, especially for large inputs. In Python, where strings are immutable, you can use lists to achieve better performance. Always demonstrate your ability to handle edge cases, such as empty inputs, strings with only spaces, or strings with no spaces at all. This attention to detail is something interviewers often look for. Finally, be prepared to discuss trade-offs. For example, while a stack-based approach might be easier to explain and implement, it can be less space-efficient compared to other methods. Balancing readability with performance can set you apart. This problem shares similarities with several others on LeetCode. For instance, LeetCode 344, reverse string, is a simpler variation that involves reversing the entire string rather than individual words. Another related problem is LeetCode 151, reverse words in a string, where the task is to reverse the order of words while carefully handling multiple spaces. LeetCode 186, reverse words in a string 2, is more challenging because it requires modifying the input string in place to reverse the word order. Lastly, LeetCode 541, reverse string 2, introduces the complexity of reversing specific segments of a string based on given rules. When considering alternative approaches to solve these problems, the two-pointer method is a popular choice. In this technique, you use two pointers to identify word boundaries, reverse each word in place, and adjust the string. While this method is space-efficient, requiring only O(1) extra space, it can involve more complex pointer management. Another option is the stack-based approach, where you push words onto a stack and then pop them off to rebuild the reversed string. This method is intuitive but uses additional space, as it requires storing all words in the stack. A modern and concise alternative is the functional approach, leveraging tools like Python's list comprehensions or the map function. Here, you apply the reversal operation to each word in a single line of code, making it a cleaner and more elegant solution. For example, you can split the string into words, reverse each word using a lambda function or slicing, and join them back together. While this approach is highly readable and easy to implement, it does come with trade-offs. Specifically, it is not suitable for in-place operations, as it creates new data structures during the process. In terms of complexity, the functional approach has a time complexity of O(n) and a space complexity of O(n) due to the intermediate storage of words. Regardless of the method you choose, it's important to weigh the trade-offs between code clarity, time efficiency, and space usage to find the best fit for the problem's requirements. Great job! We reviewed the solution for reverse words in a string 3 and discussed different approaches. Remember the key takeaways and keep practicing similar problems to strengthen your coding skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!